Assalamualaikum and hi everyone. So now we continue about stability. So in this slide, I will show to you several examples that can help you to understand how to apply Routh-Hurwitz technique to determine the stability of the system. For this example, this is a closed loop system where the GS for the system is 1000 divided by S plus 2 times S plus 3 times S plus 5. So this is a unity feedback system. So in order to apply this Routh-Hurwitz criterion, first we have to simplify this block diagram until we get only single block diagram. So in order to do so, we can use this formula. This is a formula for closed loop system. So where we just put this GS into this equation here, and then divide by 1 plus GS. Also, we just put this equation here, this transfer function here, and then we time with HS. HS in this case, because this is a unity feedback, unity means 1. So HS in this case is equal to 1. So after we solve this, we get a single block diagram like this. And then this denominator part, this one, when we put this equal to 0, so this is a characteristic equation for the system. Okay, based on this characteristic equation, we can complete this RH table. So for the first row, we can complete by take odd coefficient of this characteristic equation. The odd coefficient of this characteristic equation is 1, 31, and after this 1030, there is no coefficient, we just put 0. So that's mean we just put here 1, 31, and 0. So for the second row, we just take the even coefficient of this characteristic equation. So the even coefficient is 10, 1030, and also the rest is we just put 0. So we just put here 10, 1030, and 0. Okay, this one 10 and 1030 we can simplify by divide both with 10, and then this one become 1 and 130. Also you can it's up to you, either you want to simplify this or not. You can remain use 10 and 1030, and then you will get the same answer, because the important thing with this analysis is we just to we just to investigate this first column, either there are sign changes or not. So for the rest row, we just use the formula that we have discussed before, and after we apply that formula, we get this first column equal to negative 72, and the next this column equal to 103. So based on this, we can simplify like this. So based on this, the first column, we can see that there are two sign changes occurs. One from this to this, so from positive to negative, and another one is from here to here, from negative to positive. So based on this, we can know that there are two poles that are located on the right half plane. So based on that information, so the system is said to be unstable. Now let us look at another example. So with the help of root table, determine whether the polynomial equation, this equation, is stable or not. So same like previous example. So this equation we can consider as a characteristic equation of the system. So based on this equation, we can complete this RH table. So where for the first row, we just take the odd coefficient of this from this equation. So the odd coefficient is 1, 3, and 20. We just put 1, 3, and 20 in this first row. So for the second row, we just take the even uh, coefficient of this equation. So the even coefficient is 2, 4, and 0. Because there is no coefficient after this 20, we just put 0. So that means this one is 2, 4, and 0. And then after that, we just apply the formula that we have discussed before. So we can get the value of A0, A1, A2, B0, B1, and so on. Okay, after we calculate, so this value A2, A0 is equal to 1. And the value for B0 is equal to negative 36. And the value of C0 is equal to negative 720. Okay, the other value you can check here. Okay, so because in order to check either the system is stable or not, we just focus on this first column. So based on this first column, so from here to here, there is no changes happen to this to the sign. Also from here to here, so because this one is equal to 1, so that means there is no changes happen. From here to here, because this one is negative, so this one is positive. So from here to here, there is 1 changes happen. And from here to here, because this one is negative and this one is also negative, so that means there is no changes happen. So that means there is only 1 changes happen in this first column. So that means there is 1 pole located on the right half plane. So that means the system is not stable because there is pole located on the right half plane. So the same method can also be used to determine the range of stability of a closed loop system that has a gain K. So now let us look at an example of how we can analyze the system with unknown K value. K value means gain for the system. So for example, we have a unity feedback control system with this open loop transfer function Gs equal to K divided by S times S square plus 2S plus 5. So before we can analyze the value of K so that the system is in stable condition, so first we have to find the characteristic equation of the system. So to do so, we just simply solve the closed loop system by using the same formula as we discussed before, which is Cs over Rs equal to Gs divided by 1 plus GSHS. So because this is a unity feedback control system, so that Hs in this case also equal to 1. So by doing so, we can obtain the characteristic equation for the system. And then from that characteristic equation of the system, we can use RH table to find the value of K so that the range of K that we choose is make the system in stable condition. So to do that, in order to get the characteristic equation for this system, we just use this formula. So where 1 plus Gs Hs equal to 0, so we just put this Gs in this formula. And then as I mentioned before, Hs is equal to 1 because this is a unity feedback control system. So we just put all this in this equation and then we get this results. So based on this result, after we rearrange this result by simply make all the denominator for this component and this component equal, so we get the answer S times S squared plus 2S plus 5 plus K equal to 0. Okay, the denominator component we transfer to this side. So after we transfer, we just simply multiply with 0. So the answer becomes 0 in the right side. So that the characteristic equation of the system become S power of 3 plus 2S squared plus 5S plus K equal to 0. Okay, from this characteristic equation, we can identify, we can investigate what the value of this k so that the system is in stable condition. So in order to do that, first we have to come up with this RH table. So how to come out this one? So the procedure is same like what we have discussed before. So first we just fill in the first row by taking the odd coefficient from this characteristic equation, and next we fill the second row by taking the even coefficient from this characteristic equation. Okay, so the next coefficient, we just use the formula that we have discussed before, where this coefficient time with this coefficient minus this coefficient time with this coefficient divide by this coefficient, the result become 10 minus k over 2. And also for this one, and also this one. And after we get all these coefficient, after we fill in all this in this RH table, so we can analyze, and then we can know how to choose the value of k so that the system is in stable condition. So as I mentioned before, so in order to make sure the system is in stable condition, so we have to make sure all these coefficient should be in a similar sign. So in this case, this one is positive sign. Okay, the second one, this one is also positive sign. So that to make sure the system is stable, so this coefficient and also this coefficient should be in positive sign. So how to do that? So first we just take this one k. So in order to make sure this one is positive sign, we just put k is greater than 0 like this. Okay, when we put k is greater than 0, for sure this one is positive. Okay, next we take the second lowest or the coefficient here. So this component also must be greater than 0 so that this coefficient is positive. So we just put 10 minus k divided by 2 is greater than 0. Okay, from this equation we can know the value of k. So from here we just put 2 here, and then the equation become 10 minus k is greater than 0. And after that we just put this 10 here, and then we get negative k is greater than negative 10. So we can eliminate this negative sign by time both side with negative. So the result become k less than 10. So based on this result, k less than 10, and also based on this information and based on this result, so we can conclude that the system will be stable if k between 0 and 10.